Hi there! In this video I'll be introducing Task, a library made and best used with TypeScript that will make our apps more robust by allowing us to type the errors of our asynchronous code. As I always say, if you only type on success, you're missing half the fun. We'll start by speaking about promises and abstractions in general using some contrived examples. Then we'll see why promise can be typed on error using TypeScript, which will lead us to introduce Task. And finally, we'll see a real example from our codebase that will help us understand the benefits of typing our errors. A promise is an object that allows us to abstract the code from time and error handling. In this code, we have the int function, which only deals with numbers. If we pass a number, we'll get the successor. It doesn't have the notion of time, and it doesn't have the notion of errors. The int function doesn't care if we resolve the promise immediately or after 1 second. Furthermore, if for some reason we couldn't get the number, because let's face it, asynchronous code may fail and we should expect for failure, the code won't blow up in our face because the int function won't even be called, and the promise chain will continue in the error side until it reaches a catch, or the second argument of then. Abstractions in TypeScript are modeled with generics, so when we say we have a promise, we say we have a promise of something. We have a promise of t, in this case, a number. Notice that we didn't specify the type. We rather let TypeScript infer it for us. Having generics is great because they give us guarantees for our abstract code. If for some reason we made a mistake, the TypeScript compiler can warn us that we are probably doing something wrong. But as we can see in this part of the code, which only purpose is to allow us to inspect the promise type, the success value is correctly typed as number, but the error is typed with the general type any. So all the guarantees we have when things go as expected are lost when things go south. And as they say, if anything can go wrong, it will. So why aren't promises typed on error? The short answer is that they can't. Let's see the next example to see why. In this code, we have the int function and its cousin, the int that may fail. Promises have two ways to inform that something is not right. The idiomatic way is to return a rejected promise, in this case of a string, but we could potentially reject with an error object, a number, a boolean, or any JavaScript type. If we only had this way, we could easily type the errors. But sadly, the other way a promise can fail is if the function throws also a string, a number, or an error. If that happens, the JavaScript specification says that the promise will be rejected with the thrown value. And because TypeScript doesn't have type exceptions and our code or the code that we call could potentially throw anything, TypeScript is forced to type the errors with the general type any. So, until we have type exceptions in TypeScript, we could either drive blindly on the error side of the road, or we can use tasks. Tasks, like promises, are a way to abstract time and error handling, but unlike their counterpart, they are typed both on success and on error. The reason we can do this is because we are not tied to the promise specification. The main mechanism to inform that something went wrong is to return a rejected task. And if for some reason our code, or the code that we call, throws, we wrap the value into an unknown error object, as we'll see in a moment. Given the fact that we are not bound to the promise specification, we decided to tweak other things as well. First, notice that tasks are parameterized in two types, the success and the error. We can see that T1 is inferred to be the type number never, as task resolve can't fail. Instead of having one then method that does 3 different things, we separate each behavior into its own method. So instead of then, we have map chain, and fork. You can read more about this decision in the documentation, but for now, let's use our intuition. Map is like arrays map, or ArcGIS map. It is used when we want to transform our eventual value. In here, we use the pipe operator to allow us to inspect the types of the underlying task, but we'll see other uses in a minute. As you can see, the task has changed from number never to number unknown error. This is because we cannot guarantee that the ink function doesn't throw. The second use of then is if we want to call another asynchronous operation, or we know that what we are doing may fail. When that happens, we can use chain. Notice here that TypeScript can infer the type of ink that may fail, and now the error is of type string or unknown error. If we decide to change our error type, the error types are updated accordingly. We could also catch a particular error, and TypeScript will remove it from the possibilities. The third use of the then method is when we want to do something with our eventual value. For this, we use fork. There are two differences to notice. First, that the error callback comes before the success. This forces you to always check for errors, even if you are just going to log them or ignore them. The other one is that, just like ArcGIS, tasks are lazy. So if you don't fork a task, nothing happens. By doing this, another common problem with promises is resolved. Notice that if we run our first example, we get an unhandled promise rejection error, even if we don't use the promise. Using task, if you don't fork, nothing gets executed. And because errors are the first callbacks, you need to explicitly ignore them. The last method we'll talk about in this section is the pipe operator, inspired by ArcGIS. So far, we use this to see the underlying type of our task inside a chain, but it's way more powerful than this. This method allows us to use the open-close principle. Tasks are open for extension but closed for modification. The idea is to maintain the surface API for the library very small, but still allow you to create as many operators as you want. In fact, the only operator not covered by this video is task_all, which works exactly like promise_all. In this example, notice how we create new operators by composing the existing ones. All that is necessary for this to work is to have a function that receives and returns a task. Also notice there is a sister library called tstask/utils that withhold common operators used to manipulate tasks. For our final section, let's see a real example using our codebase at Akamica. This is a Node microservice in charge to convert a list of applicants into actual students. Sadly, most of the helper functions you'll see here are closed source, but they heavily use tasks, so you'll get an idea of the possibilities. The first thing I want you to notice is the few amount of types there is for an statically typed application. At most, you can see this parameterized function here, which actually is not needed. If I remove the type, it's inferred correctly. So there's two reasons to pass the type true. The first one is that it acts as a post condition, making sure that my endpoint returns as expected. The second one is that I can read it without having to inspect the code, and I can even follow the definition. The method createEndpoint receives a function that, given the request, returns a task to the response and possible errors. In turn, createEndpoint returns a middleware ready to be used by Restify. If we check the definition, we can see that the task is of type T, which can be a string, an object, or an HTTP response in case of success, and an unknown error or HTTP error if anything goes wrong. The unknown error is treated as a 500 error and is properly logged. The HTTP errors contains the status code and a possible message to return. By having the createEndpoint function restricted on errors, the compiler will fail if we don't say how we want to treat a particular situation. With the use of this catch, we can check what's the error on every step of the chain. After the first step, the one that checks that the request has an authorization header with a valid user, the error can be one of the followings. First, unknown error, because functions may throw. Second, problem reading secret, which will happen if we can't read the secret file from the swarm. This file allows us to connect to the database and decrypt the access token, which in turn is a composed error, because maybe the file doesn't exist or is not a valid JSON, etc. The third error is database error, because maybe the connection is done or the query is invalid. Finally, unauthorized error, which is one of the possible HTTP errors and has a status code of 401 if the token is invalid or if it doesn't correspond to an active session. If the first step is successful, notice that the request now holds the user information. The second is an authorization step. Basically checks that the user that makes the request has access to do this. If it doesn't, now we have a forbidden error, which is also an HTTP error with the status code 403. The first step checks the request body. Once again, notice the lack of types and the power of the type inference. Update batch applicant body is a contract, as defined by another open source project called Parmenides. This contract defines the form of the JSON received, in this case an object with two properties, a status that can be one of the following string literals, and applicants, which is an array of numbers. We can check the inferred type here. If the body has the shape that we want, then the request will be typed accordingly, and we'll get type safety. If it doesn't, then we'll have a bad request error, which is another HTTP error with the status code 400. After we batch accept or reject the applicants, we may have another 3 additional errors. No patent commission and applicant not found are treated as 404. And commission doesn't have location would mean that our database is not consistent. So if that happens, we want to send a Slack message that we can check to see what's going on and fix it. The errors that we don't care, we explicitly convert them to unknown errors, so that create endpoint can respond a 500 error and log it. So this is basically it. Remember that the idea behind a static type checker such as TypeScript is to help you cut possible errors before they hit production, and trying to stay out of the way by having as few explicit types as possible. I hope you like this video. If you have any question or feedback regarding task, you can comment this or send me a tweet. On the GitHub page, you can also send your log or file an issue if you see a problem. Bye!